So let's dive in with examples. We already basically know how to solve exponential equations. We just need to do some examples of this to drive it home. So we've solved equations like this already. 4 to the power of x equals 9. And when we were first introduced to such equations, we solved them by taking the logarithm of an appropriate base. The first way we approached these equations would have us take the log base 4. However, there were practical problems with that. There's no log base 4 button on the calculator. You would have to use the change of basis formula if we wanted to proceed like this. So as of yesterday, we presented another way to approach these problems. We can take the logarithm of any base. In particular, either the common logarithm or the natural logarithm. And the point of using the common or natural logarithms is that we have a common logarithm button and a natural logarithm button on our calculator. Now, if we use a logarithm that doesn't match the base of the exponent, a log base 10 here, an exponent of 4, then the common and logarithm, and the exponential function don't cancel out. But according to what we discussed on Monday, taking the logarithm of a power brings the power down in front of the logarithm. And now we've got x times a number equals another number. We can use division divide both sides by the log of 4. And there's our answer. In almost any applied setting, we're going to want a decimal approximation. So let's get to that. The common logarithm of 9 divided by the common logarithm of 4 x equals 1.58496.3. So we've done problems like this already, and that's basically all this section is. We're just going, well, that's not true, but that's basically all today's lecture is. We're going to look at these examples. We'll add some complications, and we'll see how to deal with those complications. For example, 2 plus 3 to the power of x equals 9. Now, we must be careful here. A common mistake people make is to see this exponential and take the common, or take a logarithm of both sides. And this isn't a mistake in the sense that it's an incorrect thing to do. If this equals this, then this does equal this. It's a perfectly valid equality. It's a mistake because it's a useless step that doesn't help us. We know how to take the logarithm of a product. We know how to take the logarithm of a quotient. We do not know how to simplify the logarithm of a sum. And in fact, the answer to that is that we cannot simplify the logarithm of a sum. There's no way to simplify this logarithm and get x by itself. So this is a true thing to write, but it's not a useful thing to write. We need to get rid of this addition before we take a logarithm. And once we've made that observation, actually doing it is relatively straightforward. Addition is eliminated via subtraction. We can subtract 2 from both sides and get 3 to the power of x equals 7. And now we've done problems that look like this before. In fact, we just did a problem that looks like this. So we'll take the logarithm of both sides now that we've gotten rid of that addition. And And just for the sake of variety, the last problem we did, we took the common logarithm of both sides. This time around, let's take the natural logarithm. And I mean, that doesn't change anything fundamentally. Any logarithm, whether common or logarithm or a totally different base, will take an exponent down in front. X times the natural log of 3 is the natural log of 7. And now I've got, let me move this document camera just a bit. We've got multiplication. X times a number equals another number. Multiplication is undone via division. And this division just done on our calculator. We're using the natural log this time, so we're pressing the LN button. And we get 1.771244, rounding rather arbitrarily to 6 decimal points. Let's do a third example. This time, let's complicate the exponent a little. So let's say we have 4 to the power of x minus 2 equals 3. So this looks like a lot like something we've already done, or the type of problem we've already done, I should say. But instead of having an x up here, we have an x minus 2. That's fine. That is not a fatal problem. Even if our exponent is more complicated, we can simply take the logarithm of both sides, and that will bring our exponent down in front. Now, there's a mistake that students make here, which is as follows. Bring the exponent down like so. So the exponent is in front. Then we have subtraction. Let's add this to both sides. But as I say, this is a mistake. When you bring the exponent down, the exponent needs to be in parentheses. Because you're multiplying the entire exponent by the natural log of 4. Without the parentheses, you're only multiplying a part of the exponent by the natural log of 4. This -2. Once you have your parentheses in there properly, you see that what we have here is multiplication, not subtraction. And as such, it's eliminated using division, not addition. And this really is subtraction. X minus 2 we can add 2 to both sides of the equality. And again, we almost certainly want a decimal approximation. The calculator will follow the order of operations correctly. So it will do this division before this addition. And we get x equals 2.792481. Let's do another example. This will be, I think, the last example that isn't a word problem, because I think if you do too many examples in a row, it just becomes tedious and learning no longer occurs. Let's approach a really relatively complicated example such as this. Our ultimate goal is going to be to take the natural logarithm, or the common logarithm, or just a logarithm of both sides. But when we take the logarithm on the left-hand side, we'd like to only have this. We'd like to only have the exponential. We don't want this addition. We don't want this multiplication. So let's get rid of both of those things, and we're undoing the order of operations here. So addition is the last thing that happens here, making it the first thing we want to get rid of. And now we should probably get rid of this multiplication. We could just take the logarithm of both sides if we wanted to. Because this is the logarithm of a product, and we can break the logarithm of a product up as per the last section, and then we could work with this. I think that's making things complicated for no real benefit. It costs us basically nothing to divide both sides by 4 and get rid of that multiplication before we take a logarithm. And now we can take a logarithm. I know this is a kind of lengthy problem. Just give me a shout in the chat if there are any steps you're not following. We can take the logarithm of both sides. On the right, this is just some number. On the left, that x plus 1 comes down. But it comes down inside parentheses. So we have multiplication here. And multiplication is undone via division. Finally, this is undeniably, as I said before, a kind of lengthy problem, but we're just about done. All that remains to get rid of is this addition. And addition is eliminated via subtraction. Again, your calculator will do the order of operations correctly. It will do the division before it does the subtraction. You don't need to tell it to. And we get x equals negative 0.490616.